Very simple example this time around. Fibonacci sequence. Super easy to define recursively, which means, of course, in a language that handles recursion as well as OCaml does, very easy to define. This is straight out of any old textbook. Easy. Test this quickly. We've got all the Fibonacci numbers. Really simple. Also kind of problematic. As an example, if I want to calculate the 100th Fibonacci number. Easy, right? Okay. Now, I'm going to get bored while that process is. So, let's talk about memoization. We need something to hold memos about what goes into a function and what comes out of it. Because otherwise, the Fibonacci sequence, when we calculate that, it'll calculate the same values many, many times as it goes through. And the performance, the complexity becomes quadratic and takes forever. So I'm going to just use a very simple map functor. Generates a module fold that can map integers to any other value. And now we're going to have our Fibonacci function take another argument, a memo argument to update. So if, pretty simple, if similar start here, if n is 1 or n is 0 or n is 1, then very simple, it's n. Otherwise, we're going to look up in the memo. And I'm using the findopt function, which returns an optional value, so we can use pattern matching on it to determine if it found anything or not. There's a regular find, which throws an exception if it doesn't find it, which would be perfectly valid, but I don't feel like doing that today. So if it finds a result, the answer is just going to be the result, except we also need to pass out the memo so that it's getting passed to the next recursive call. That'll keep everything nice and type safe. So if we don't find anything, now we need to calculate it. We can't quite just type it out. We need to capture the memo that's coming out of the recursive call. So we'll call that memo coming out, memo prime. We really wouldn't need to necessarily, but we can. So we'll call this with, we're going to pass in the existing memo and n minus 2. And then we're going to get our second result, called r prime, in this case just for the sake of it, and the updated memo, and we're going to take that memo prime and add to it for n minus 2. We now know that the result would be r. So that gets added to it, and then n minus 1. Now, we know that the result is r plus r prime, and we're going to take that and we're going to actually add a couple of things to it. So we're going to say so we know now for n minus 1, we can add to the memo. Be careful about precedence. Add for that. We're simply going to add that r prime is the result. We're also going to add that for n, we now know it is r plus r prime is the outcome of that. So now we have a new memo built up, and all this information is getting stored away. Okay. So where did I go wrong here? Because I didn't pass out the memo in this initial call. There we go. So now, if we pass an empty map to start with and 100, oh, there's an immediate response. Of course, we got back the memo as well, which we don't really need, so we can wrap all this up. But if we actually want to take a look at that memo that comes back, we can look at the bindings from that map. And we need to look at just the second member of the tuple, and there we go. So we can actually see. Now, as I noted before, we've run, you can see from the negative numbers, we've run some integer overflow issues, which means we got the wrong answer, but really fast. We could even do a much larger number here and get a very fast response. So again, it calculated the wrong thing, but it calculated it very fast. Fib 100 is still running on the other side. Hasn't found an answer yet. So let's take this whole function and wrap it up a little bit nicer. So we don't have to see passing the memo along. You don't really need to fix the indentation, but I'm going to because I'm just picky that way, I guess. So if we come down, we can now just say we're going to call that. And we can also then take that and discard the second element of that tuple, which is the map, and boom. We don't need to provide anything else. Very, very fast. We could even, if we still had that explicit memo argument that we were passing, we could save the memo from a previous call and pass it in, and it would have to do almost no work at all. Just 2 lookups on the map, add them, and done. So that's extremely effective way to streamline things. Now, another problem that we can run into in programming, there's a common challenge problem, which is to take a number and figure out the smallest number of squares that it takes to contain that other number. So we need a couple of different things. So we can check if something is square by, well, we're going to define a round function, because floating point numbers and integers in OCaml are 2 separate things. And of course, if we take the square root of something like 169, we might not get 13. We might get 12.999999997, or we might get 13.000001, and then when we convert from that number to an integer, we get we get the wrong answer, because it's just going to take the integer part. So if it's at 12.9999997 and we can just naively convert to an integer, we get 12, which is wrong. So we're going to add half to n, and then we're going to convert it to an integer. So we're going to end up with taking that n, finding its square root, rounding that, and we're going to call that r for root. And check that r times r equals n. Something didn't quite go right there, so let's just double check that our rounding function does what we think it does. Yes, so perfect. So I'm just going to use some different names here. I'm not quite sure why it thinks. Ah, right, of course, this is on me. We need to convert that n, which is an integer, to a float before we can provide it to square root. So that works. Perfect. Now, the next step we need to, of course, have is we need to determine all of the squares below a certain number. And if n is less than or equal to 0, then there are no squares below it. Otherwise, if n is a square, then we're going to tack n onto the front of the result of checking n minus 1. Otherwise, we're just going to make that recursive call. So if we check this out real quick, so we get those are all square numbers. So in order for us to find the naive way of finding all those numbers that'll fit squares is pretty straightforward. We're going to need to take a look at, obviously, if n is a square in the first place, then it takes 1. There's no shorter, there's no simpler solution than that. Otherwise, we're going to take a look at all of the squares below n, and we're going to map those. So for each of those, I'm going to call it x to keep it separate from n in this case, we're going to tack that. So for instance, if we were given 18, the next square below that would be 16. So we're going to take that square and we're going to add it to the result of finding the minimum number of squares that can store the next little bit that's left. So in the case of 18 minus 16 is 2. So what's the minimum situation to store all of those? Now, of course, 18, the next thing down would be 9, and we'd be left with 9. And then it would also check, 4, and it would say, okay, 14's left. What we really want to find is, so it would generate a whole bunch. This is going to generate a whole bunch of different lists. And we want to find the shortest one. So what we're going to do is we're going to sort those. And we need a comparator function. So we're going to say, we're going to compare the length of A and the length of B. There's our comparison. And now we're only going to want the shortest one, so we're going to take the first one, the head. Easy. Now, to test this, we were talking about 18. So 18 shouldn't return 16, 1, and 1 because that's longer than 9, 9. So let's find out. There we go. Easy. This is a very, very simple, straightforward solution to that problem. It also will fail every single time because it's, again, like the Fibonacci one, it's doing a lot of work over and over and over again. And that's excessive. We don't need to do that. So if we tried it with a bigger number, we're going to notice it's going to take a very long time. So instead, we're going to take some of this other code and copy it, so I don't have to rewrite it. There's no point in doing that. Over here, and we're going to try memoizing this function. So by memoizing it, we're not repeating that same work over and over again. And in this case, just for fun, I'm going to use a default argument, which would just like say, for fun. So in this case, I'm going to say, we're going to take a look and find, is it in the, does it already exist? Have we already calculated this? If we haven't, but if we haven't already calculated it, but n is less than or equal to 0, then we're really empty list. There's nothing. But we're going to make sure that we know that's the case by putting a memo up for ourselves. If it's not in there, but what we're looking for is a square already, then we know the answer is just that single length, and we're going to again update the memo. Very simple. Now, of course, the trick is it's not that simple in this case, so we're going to recalculate. Looks fairly straightforward so far, very similar to what we had, but we can't map because the maps, it doesn't maintain any information between calls. So instead we're going to do something called a fold, which builds up, iteratively builds up an accumulator, and that accumulator can include our memo. The second argument to that function we're passing to the fold is going to be each square below n. The accumulator is the first argument, so there's going to be a list and then the memo in that list. So here's where we're updating the list by saying, okay, we've tacked on the minimum number of squares for that, but we're also going to want that updated memo in there as well. And of course, our starting point is going to be an empty list and our memo. So now we have all the lists, all the memos, everything's built up. What we really want to find, of course, is for those lists and the memo, we are going to look for the shortest thing. Now we need to find the shortest one. Give ourselves a slightly easier way to say list length we're going to take the lists and make sure I use parentheses in the right places, of course. And then return the shortest, and of course, update our memo. somewhere I've clearly neglected a parenthesis. And I think it's going to be right there. Oh. Normally I'd use a little more spacing than this to make it easier to read. So let's fix this. Ah, I see where I made the mistake. And I need to make the whole thing recursive. Keep in mind, in the other window, it's still running. There we go. Now let's try this. Oh look, instant answer. Nearly instantaneous. That's still running. We're going to try a bigger number. A very quick response, all the while the other window is still running